Welcome back, Calculus 2 students. The second half of this semester begins from 10.3, polar coordinates. This is actually a review of Math 1650 pre-calculus or Math 1600 trigonometry. Because it's a review, we're going to cover 10.3 as quickly as possible, and then we'll move on to 10.4 in the next segment of the video. That's where all the important calculus materials are located. Alright, let's go over to our review using the Mathematica notebook. And here's a visualization of rectangular and polar coordinate systems. A rectangular coordinate system is a scheme to represent a point in a plane by horizontal and vertical positions. Horizontal and vertical positions are typically expressed as x-coordinate and y-coordinate, and those are pair of real numbers, kind of like this number and that number. This program is randomized, so you can run it several times, and as you run it, please note that the new rectangles, these dotted rectangles, are forming, given by x and y coordinates, and that's why this name came about, rectangular coordinate system. Also, as you run this many times, please note that there's something else that is changing. The red one, the angle, and please note that the angle is always measured from the x-axis in counterclock fashion. Okay, let's stop here. I ran it many times already. And that angle is called polar angle, and because the angle is being measured from the x-axis is often called a polar axis. And the distance from the origin is represented as r, and the r and theta value will represent the point by this conversion formula. X comma y is equal to r cosine of theta, r sine of theta. It's pretty clear why, because the trigonometric functions cosine and sine were defined by x over r and y over r respectively. So we have this conversion formula. This is the most elementary case. The angle theta is between 0 and 2 pi, or 0 and 360 degrees, and more importantly, the r value, radius, is always positive. Consequently, it represents the distance from the origin. But not in general, we can generalize it further. We can make theta value negative or beyond 2 pi range. And also, even more importantly, we can make r value negative. What do you mean by that? Well, this is a standard case. And if I randomize more, I can accommodate negative theta value. Theta is not just 0.4475 times pi, but negative of that, so we measure it clockwise. That was relatively easy to understand. Negative r value is a little bit more difficult to see. This is the way things go. We get the position by theta value. In this case, theta value is negative 0.355 something pi, so we go over to the fourth quadrant. And then r value is negative. Consequently, we move not 1.40056 to that direction, but to the opposite direction by same amount, consequently generating this point P on the second quadrant, in this particular example. Run it again, another similar situation. The theta value is negative 0.93 something, so we should be moving toward the third quadrant, but r value is negative, so we go backward and move to the first quadrant. In general, we have this kind of conversion. R theta can be converted into x comma y equals r cosine of theta comma r sine of theta. That's the general case, and that's where everything is starting. And if we throw away the restriction, r is positive and theta is between 0 and 2 pi, we can take anything, then we can get points on rectangular coordinate plane in multiple. Consequently, coming back to the other direction can be a bit trickier. As you saw before, R value can be either plus or minus depending upon which direction we go. So it's not just square root of x squared plus y squared coming from the Pythagorean formula, but you have to consider either plus or minus. And also theta value can be tricky too. If you look at your standard triangle, then y over x is tangent, so you can look at theta equals to arctangent of y over x. But that is not always the case, because if you do that, you're going to get the angles only in first and fourth quadrants. So you may have to add pi, or sometimes subtract pi, or do something about. Or if you change r to negative, then maybe adding to 2 pi, all kind of things can happen here. So using algebraic mechanism to find out the conversion is rather tricky. So what I usually suggest to my students is to use geometrical approach. First set of problem, conversion between r theta to x comma y, that's too trivial. These are better. For example, how do you convert 3 square root of 3 comma negative 3? Here's a picture. And looks like the angle is, let's say, negative 30 degrees, negative pi over 6. And then you can use negative pi over 6. Oh, I decided to use 11 pi over 6. That's okay too. Depending upon that, you get the r value. How about some other problem here? Something like that. Okay, we can find out r value by Pythagorean identity, and then we can simply take arctangent because this point is located at fourth quadrant. If you simply take arctangent, that's going to be fourth quadrant. So if you want something between pi and 2 pi, then you have to add 2 pi. So if you use geometrical approach, then you can answer these kind of questions more effectively than using, well, this kind of rather ambiguous conversion formula, using what k value to take, what sign to take. It's kind of confusing. Okay, that was polar coordinates, and let's go over to polar curves. Let's look at some examples and let's have some fun. Polar curves are given by r as a function of theta. Because x is r cosine of theta, y is r sine of theta, we're going to have x theta is r of theta cosine of theta, and y of theta is r of theta sine of theta. Consequently, we're going to get a parametric curve. Well, here's an example of that kind of curve. We saw this curve before, as a matter of fact, but this time let's look at it in terms of polar coordinates. So let's pay attention not only to this moving particle model and this red point, but also the gray arrow that is rotating around. That represents the angle theta, the direction. And the red dot is sometimes pointing toward that arrow, sometimes it goes to the opposite. And that's when r value is either positive or negative. How about this one? Okay, again, we have a curve that we saw before. Butterfly. Let's slow it down. Again, the same deal. This gray arrow is the angle, and this red dot is moving either in the same direction or to the opposite direction, depending upon r value. R can be either positive or negative. In some cases, we can deal with a family of curves given by some parameter. And here's one such example. R is given as sine of k theta, and when k is equal to 0, we have sine of 0, so that's 0. Radius is 0. No matter what angle I'm looking at, we have to have, well, the origin, so we have a single dot. And this is the animation. Actually, nothing changes. It's not really interesting because k value is 0, so radius is 0. But if I change my k value, things are a little bit different. K equals 1, we have a circle, and again we have the same kind of behavior R can be either positive or negative. So the red dot can be either in the same direction or in the opposite direction. Whenever it changes, it runs through the origin. Another k value, we have, well, different polar curve. Still different polar curve if I change my k value. Still different polar curve. Another polar curve like that. Your k value can be negative too. Here's even more impressive picture. Limaçon. So data value can change, but let's see, the default is a equal to 0, where r is 1 plus a cosine of theta. A is 0, so r equals to 1, so the radius, the distance from the origin is constantly 1. What we just have a circle centered at the origin. That's not really interesting. So let's change the a value. Let's increase it a little bit. And we have different curve forming. Kind of like that, as a value changes. Special case when a is equal to 1, this case is called a cardioid. And when, let's see, when a value is a value is 1, excuse me, we're going to have r equals to 0 when theta value is pi. Cosine of pi is negative 1, so we have 1 minus 1. Our value is 0. Not coincidentally, when this gray arrow points toward pi, the opposite side of the x-axis, that's when the red dot comes back to the origin. When r increases further, then we have inner loop. This family is called Limaçons. R is negative, then we have the opposite side. We can animate both of them together as a matter of fact. Okay, that was fun. And let's move on to the final example. And this one, again, has a lot of, well, this one actually has two parameters. A value, kind of like Limaçons, those are real numbers, and k value, that's inside theta, so that's going to be an integer. So we can animate like this, and then we can adjust my a value. Okay, changing a value simply changes the radius of the circle. Not really interesting, but if I change k value as well, things are a little bit different. Changing a values, change the shape, change the different k values, still different. Let's animate both of them and then change k values at whim. And we have different pictures forming. We have a family of curves kind of like these. Okay, that was fun. Okay, do we have some time for an example? Let's see. Identify the given polar curve by finding its Cartesian equation. If you have done some analytic geometry, you may understand what those are, but I'm not going to impose it too much. Here's one way. R squared equals to 4r sine of theta by multiplying r to both sides of the equation. And r squared, the left hand side, is x squared plus y squared. Right hand side is 4 times r sine of theta, so r y, as a matter of fact. Okay, let's correct the problem. Sorry about that. I kind of got confused with sine and cosine. So our cosine of theta is x, so we have 4x. So if I move 4x to the other side and take complete square, we end up with, well, a circle. How about this one? Tangent of theta times secant of theta. R is equal to sine over cosine. Let's manipulate this thing. Again, we need r squared somehow, and we end up with a parabola. Well, more can be done with these kind of things, but you have to know analytic geometry a priori.